folks. Hi, welcome to SEER and welcome to the battery seminar. This seminar grew out of a concept we had last year where last year it was the inverter firing line up here with all the inverter makers and all the users out in the audience here asking them hard to answer questions. And we thought this was such a great deal that we thought we'd do it again this year, only we'd do batteries. My name is Richard Perez, and I publish Home Power magazine, and I've been living on batteries for 22 years now. So what we're going to do today is get people together from the industry and people who make the batteries, people who sell them, recondition them, the experts, if you will. And what we're going to do is very loosely structured here. We're just going to sort of go down the line, each introduce ourselves and what we do, and then we're going to throw it open to you, the users of batteries, for your questions. How do we do this? How do we not do that? How do we make them last longer? How do we make them run more efficiently? What kind of battery should I put in my system? All these questions that you may or may not have had about batteries, we're here to help you, hopefully, to answer these questions for you. So we've got a panel of people who are into it up to here in batteries, and we're going to give everybody an opportunity to sort of identify themselves, tell you who they are, what they're doing, and from there it's up to you. Whatever you want to know about cells, just ask. So anyway, my name's Richard, Home Power, and I'm going to go to Rob Wills. Stand up and identify yourself.
Okay, I'm Rob Wills. I work with Skyline Engineering from Chapple, New Hampshire, and we distribute a 5 nickel cadmium battery, which is probably the most high-tech, advanced, and absolutely the most expensive battery on the market at the moment. I don't recommend you use it unless you've got deep pockets. But if you do have an appropriate need, I think it's the best battery for the job. One of the things I like to say is when people ask what I do, like at a cocktail party or something, they come up and say, well, what do you do? And I say, I sell batteries, and I'm really interested in their electrochemistry and stuff like that. And everyone just sort of disappears. And hopefully you guys will stay. So, thanks.
Bob Hammond, Arizona State University, the Center for Energy Systems Research. We're basically continuing solar research programs, particularly photovoltaics. And I also am doing some contract work for Sandy National Laboratories, and specifically a battery survey to determine what's out there, how many of each, are they gelled, are they flooded, and what's the reaction to those batteries, for example, in terms of lifetime.
Hi, my name is Steve Harrington. I work with San Diego National Laboratories in the Photovoltaic Systems Research Group. I don't live off home power, but a lot of my work is especially in small batteries and standalone systems, for instance area lightings, where you set them and forget them. I've got a lot of background in the smaller batteries, lead antimony, lead calcium, seal batteries, gel-type batteries. We've done a lot of work analyzing the charging methods people use in these lighting systems, because in problems with if you have a small balance of system mismatch in a small system and it's unattended, unlike the home power users who take care of their batteries, these systems get neglected and the batteries fail. But we felt that it really wasn't the batteries that are failing, that maybe it's how we're charging the batteries, and we need to understand that a little closer, and that's where our program was born out of. So hopefully, if you've got questions on small standalone systems, remote applications, I can answer those. Or if you have other questions that we can't field, we've got resources in the National Laboratory. We'd be glad to write these questions down and go back and get them answered to the experts that know the answers.
I'm Rob Chapple from Northwest Energy Storage. I'm not a professional battery man. I'm not a technical advisor of any sort. I'm just a user of a product we found that works. It's a surplus battery. We take it from communication service, put it back into the home power use, get a relatively good life, and have a high efficiency factors on the recharge and discharge rates. I know a little bit about batteries, and just from actual use, not from a technical standpoint. So if there's any questions I can answer about technicalities, I probably can't answer, but I can answer basic questions on what to do what.
Hi, I'm Ron Curry. I'm from Batteries Inc. right there in Santa Rosa. Primarily market large industrial cells, flooded cells to the home power market. That's only a part of our business. The major part of our business is forklift batteries to forklift dealers and users in that regard. So we do handle the big lead. This year, as well as the last 2 years, we've been powering the solar stage and everything like that on the batteries. So you can see our truck out as you come in. So technically, a little on the weak side, but one of the things I wanted to talk about today, and we'll get to, I'm sure, is the safety and the recycling of the batteries and the, how do you dispose of and deal with what's pretty some heavy metal and plastic substances.
My name is Jim Gerious, and I'm the product application specialist at Trojan Battery Company. And deep cycle batteries are the cornerstone of our marketplace. Back in the 50s, we came up with the first deep cycle golf cart batteries, and which has allowed the market to grow quite significantly. My role at Trojan is to find new uses for the products. And although the L16 and the T105 have a reasonably good reputation in the solar market, I need to hear from the audience exactly what it is the market's looking for, what you need in a battery system.
John DeAngelo, Utility Free. We specialize in reconditioned NiCads and nickel iron batteries. So I've been around the nickel iron battery for 20 years. Nickel cadmium's been around the battery for about 4 or 5 years. So you're welcome to ask me.
All right, well, this is the panel of experts here, and every one of us up here is prepared to bore you to death with a half-hour lecture on batteries. And we took a look at this, and we've got a lot of expertise and a lot of information here, and we decided the best thing to do was to let you ask questions. That lady in the back there.
Okay, this is from a total non-entity about batteries, right? Know nothing, right? And trying to understand the problems that the electric cars are having getting going. I understand that a lot of it is the size and weight of the battery. And I am interested in knowing what technology is doing or finding what advances are being made to reduce size and weight, and in what period of time do you anticipate that this will be under control so we can have electric cars?
Okay, I'm going to repeat the question in case everybody didn't hear it. The question is, what are the new technologies for electric vehicles? What are the lighter weight, longer lasting batteries for electric vehicles? Would anybody here care to? All right, you're first up, Rob.
Okay. I have several hats. One being Skyline Engineering. Another one is I run the Tour de Sol race and the Solar Electric Vehicle Symposium on the East Coast every year. If you're interested in electric vehicles, here's a plug. Solar Electric Vehicle Symposium is at the World Trade Center in Boston, October 8th and 9th. Electric vehicle batteries. When you talk about something like one of Jim Gerious' Trojan batteries, you're talking about roughly 30 watt-hours per kilogram. Is that right? That order? Okay. We're facing a real uphill battle because gasoline is about 3,000 watt-hours per kilogram. We get there because electric motors are more efficient, we put more batteries in the car. We still only get a 100-mile range. So the key problem with electric vehicles is indeed the batteries don't hold enough energy. Near-term possibilities, NiCads are one area that could fill the bill because there are some batteries, in fact, being made by this company, Hoppico, that have about 55 currently and going up to about 80 watt-hours per kilogram current production. Volkswagen Chico in Germany uses a Hoppico recombinant seal nickel cadmium battery. One of the problems with NiCads in the long term is there isn't enough cadmium available in the world to satisfy the electric vehicle market. So a solution to that is a technology called nickel metal hydride, which you've probably heard of. The main player in this country is the Ivonic Battery Company, which is a subsidiary of ECD. They were recently given about $17 million to work on their technology by the DOE under the Advanced Battery Consortium, which is the major car manufacturers, the Electric Power Research Institute, and DOE. So that's the near-term thing that I think a lot of people in this country are hanging their hat on. The Japanese look very advanced in nickel metal hydride. Energy density is probably again around the 80 to perhaps 100 watt-hours per kilogram. And Panasonic claims that they'll have a battery on the market within 6 months in Japan. So we're watching for that too. In terms of other mid-term technologies, there's some advanced lead acid out. Electrosource has been in and out of bankruptcy for a while. They were at the show here last year, and they claim, I think, 40 to 50 watt-hours per kilogram with lead acid technology. There are some technologies also with lead acid of what's called bipolar cells, where you cut down on the number of plates you need and can increase the energy density. They may do something. Longer-term technologies, the major car companies and people around the world have pretty much hung their hat on sodium sulfur batteries, which are a high-temperature battery. I think on the whole at this point they don't look very promising for electric vehicles because they run down if they're not plugged in overnight. With all the added stuff you need to make them work, even though they might theoretically give you 150 watt-hours per kilogram, they look like being closer to 100 or 80, and you can reach that with a low-temperature technology. And also they don't look too reliable at the moment. Lots and lots of little cells in series. In the long term, probably we'll have some sort of organic lithium battery that could give us a 300-mile range car pretty easily. And that whole question, I think, goes sideways when you say the real solution to electric vehicles is hydrogen fuel cells. And come to the talk tomorrow afternoon in the hydrogen session.
Wait, can I add to that? I think in the marketplace today for electric vehicles, what Rob's saying is basically true. But there's this seems to be this shroud that there's this magic power center somewhere off in the wings waiting for the electric car to come to the batteries. I believe personally that's not true. The thing about lead acid batteries is yes, they're heavy, they're lead acid, they're environmentally friendly. 95 to 98% of spent batteries get recycled to make new lead acid batteries. I have people call me every day, T105 type of batteries, T125 type of batteries. They're averaging 60 miles an hour, getting 125 miles in range, which is completely adequate for their needs. The thing about the lead acid battery is that it's here today. We don't have to wait to motivate the car. And I think, Dan here from Sunbelt Batteries, they have a converted car in Gia that did 114 miles and an average speed of 65 miles an hour between Phoenix and Prescott, Arizona. There's another whole issue that doesn't get discussed. I don't know if it's going to get discussed here or not, and that's infrastructure. What is the infrastructure going to dictate? Okay, so first of all, we're doing research on the bipolar battery. The bipolar battery is not new technology. There's a number of stumbling blocks that are going to come. We're looking at, hopefully, if we can overcome those stumbling blocks, it's 2 to 5 years before we see a bipolar battery. So from that perspective, the information that I'm getting around SEER this weekend is that, yeah, the lead acid batteries, at least, that it's allowing us to get on with getting on. But my opinion is it's going to take a concerted effort between the motor manufacturers, the battery manufacturers, the controller manufacturers, to develop an optimum system.
Okay, anyone else like to comment on EV batteries? Okay, I'm going to take my shot and echo what Jim said. It's like buying a computer. If you wait for the ultimate computer, you will never own one. It's just the battery technologies are moving, they're changing constantly. We don't have the ultimate EV battery now, but we do have stuff that works. Lead acid cells, the fiber nickel cadmium, even nickel iron batteries are being employed in electric vehicle service. So the point is, we have serviceable technologies now. We'd certainly like to have greater energy density. We'd certainly like the batteries to become more environmentally benign. But the bottom line is, right now, you can go out and run an EV on existing technologies. And I just don't want anyone to be discouraged in getting into electric vehicles because they're waiting for the ultimate battery technology. If you wait for the ultimate battery technology, you will wait a very long time because it's never going to happen. It's a series of constant improvements. So anybody else? Come on, John?
Yeah, just again echoing what Richard said. I owned an electric vehicle for 7 years, and I had lead acid batteries, and if I'd have kept the vehicle, I would have changed them. But at any rate, you know, the only reason why I got rid of my electric car is that the circumstances changed, and I wasn't, you know, it wasn't drivable within my range. But I would say, you know, 90% of us out there can use a car that can go 100, 125 miles in range for a lot of different things. So the next one you buy, perhaps they'll have these little flashy batteries, but you know, for now, let's get on with it.
There's no reason why a car you buy now with lead acid batteries couldn't be retrofitted with a more advanced battery in 5 years' time anyway.
Sure, and run better because of it.
Must be smaller by then anyway.
There you go. Okay.
I was kind of wondering, through Richard, most of us, or through Home Power anyway, which is largely Richard, a lot of us have been introduced to nickel cadmium batteries, and we seem to be getting some conflicting information about life cycles as far as depth of cycling goes. Now, like the standard T105 is rated for something like 630 cycles to 80% depth of discharge. We've basically been told that NICADs basically don't care how deep they're cycled. I've now seen some charts that imply that a NICAD does care very much how deep it is cycled. And I've seen one, I think it was in the new Alternative Energy Source book Derivative puts out, that shows a chart from Saab, Nike, I think, showing 500 cycles at 80% depth of discharge. You're getting 20,000 at 20%. So I'm just wondering, is there more information available now?
Okay. I'll pick up on that since I was the one who published that data. I am saying that an alkaline battery in good condition in home power service will give you a minimum of 3,000 deep cycles. I'm extracting this information from home power readers and from our own research. Here is some of the anecdotal information that I've been getting. I was back at the Midwest Renewable Energy Fair in Amherst, Wisconsin not long ago, just about, 8 weeks ago. And I talked to a number of farmers who had REA Days Jacobs wind electric systems, 32-volt systems, employing nickel-iron batteries. And they're still using the same batteries that were installed in these systems in the late 30s. So the point is, and when the manufacturer makes a battery, they test it in a certain fashion. And usually the charge-discharge rates are much higher than we experience in home power systems. For instance, Jim, for example, what is Trojan? You guys rate your cells at a C7 rate, C5, what?
C20 rate.
C20?
All it asks, as far as I know,
For most
I know where it goes.
is C5.
We rate the batteries in C20, and we also rate them at 75 amps in accordance with the Battery Council International specifications.
All right, well, the point here is C20 assumes that we're going to empty this battery in 20 hours. A normal home power system is sized for days of storage. We are running very light current density through these batteries.
Let me just clarify that, okay? One thing that they don't tell you when they bring this stuff up is that the difference between C20 and C100 is only a matter of 2 percentage points. Once you get beyond a certain point, you actually approach the normal internal self-discharge characteristics of the battery. So the difference between C20 and C100 is only 2 or 3% of the battery's total capacity.
Right.
But the difference between a C5 and C20 is much greater.
Is much greater.
Well, but then you got to define what a C5 and a C20 is.
Okay. The point I'm trying to make here, not being very successful in making it, is that we are using these batteries in ways that were not originally intended or even thought of by the makers.
Exactly.
So the feedback that I'm getting from the field is that alkaline technologies are incredibly long-lived in comparison with the lead-acid technologies, which is a good deal because they're incredibly more expensive than the lead-acid technologies.
Yeah, okay.
I know some of them don't worry about that.
Yeah, I think there are a lot of really interesting things about this. First off, we won't shoot Richard totally down in flames, but the first one is, how can we tie down what the different use is? Typically, alkaline batteries are used in more float-type service for telecommunications and so on that are spending the whole of their life virtually not cycling. Another major use of the batteries we get, that John gets, are and trains, and I guess they supply train lighting and things like that, and presumably they spend the majority of their life up at full charge and not cycling.
Yeah, standalone app, and then there was backup to the railroad crossings, backup to that application.
Okay, so it's again
a float service
right.
situation.
And so I think one consideration with taking those sorts of pocket plate nightcats and putting them into a cyclic service is how deeply are you actually cycling them? If they've been used in float service and they're rated for 25 years of use, that's fine. If you try and get a small NICAD bank and you work it really hard, so you cycle it every day 100%, it's going to wipe out. There's no doubt about it. Even these ones won't last forever if you do that, the pocket cells. So the first thing you've got to look at is what is your depth of discharge. I think one reason why we've had so many success stories with both new and recycled pocket plate NICADs is that people have used very large banks and they've been cycling them pretty shallowly, perhaps 10 or 20% a day. And at that rate, you can still get very long life out of a NICAD. The issue of life of NICADs is controversial. It goes back, if you want to read some of the literature, the classic book on NICAD batteries is Alkaline Batteries by Falcon. And you read the section in there on the life, and he's not definitive. He says some reports are very long life and some are short. And you read the Saab knife documentation, and you'll see 500 complete cycles, which puts it about the same as a lead-acid battery.
Rob, I think his point here is depth of discharge. I think that's the biggest variable in any battery, whether it's lead-acid technology or alkaline technology. But again, from experience in the field, I give the edge to alkaline technology.
Sure.
Just, you know, from what I've seen.
Right. So that's my next point. What is the failure mode of alkaline batteries? And what's the failure mode of lead-acid batteries? I think this is a key point. And what is the definition of end of life? The end-of-life definition for an alkaline battery is where it's down to 80% of its original capacity. The end-of-life definition for a lead-acid battery is where it's only useful as a plant or as a doorstop. And that's a very significant change. If we could...
Let's tell the truth. According to BCI standards, for the T105 battery, the end of life is when it fails to produce 40 minutes of a 75-minute discharge. Okay? That's failure point. Okay. For a lead calcium standby power system, when the battery fails to produce 80% of its rated capacity, that's end of life. Okay. Which is no different than the nickel cadmium.
Industrial cells, 80%.
Yeah.
Well, right. There's one difference because of the electrochemistry. When your lead-acid battery is at 80% of rated capacity, its self-discharge has gone up considerably, and you know probably that sulfation is really setting in. The battery is going to be less efficient and perform basically poorly. A good example of that was a hydro system where I replaced 8 large lead-acid batteries recently with fiber NICADs. They had so much self-discharge with an 8 amp continuous 12-volt hydro charging system, the battery system never got over 11.5 volts. And so its self-discharge was such to absorb all the energy that was being generated, and it just sulfated up more and more.
Wow.
We have
like 80% about 3 years ago on it.
Right. So I'll just let me make my final point. My understanding is that the end of life of a NICAD is a result of crystallization of the active material. You end up with less effective material available to the electrolyte. You end up with a reduction in available capacity. And the battery is still usable and still has basically the same electrical characteristics. Whereas the end of life with a lead-acid battery, you've got sulfation, you've got, because of the construction, base material falling off the place.
I mean, the chemistry and all that acid, that's the way it goes.
That's right. At the end of life, it's the end of life. Whereas chances are, with a NICAD or a nickel ion, you can keep using it when it's down to 50% capacity and it'll still be performing efficiently.
Provided you don't need to go to a 75% depth of discharge to that you need to do it.
Yeah.
Yeah, absolutely.
In one side instance, you don't.
Correct. No, you go ahead.
I mean, we're getting into the crux of one of these issues that keeps continuing and being on the sort of the lead acid side of the home power market rather than the nickel cadmium. I think we have to look at lot of different things to try and compare these things. And one of the things that I don't see evaluated very often is the idea of, are you using this battery as a float-type battery? In other words, are you on hydro? Do you have a big battery for the amount of charging you have? Or are you in a hybrid system where you're cycling your batteries deeply? Whenever anybody says, oh, my system's great, it does this and this and this, you never know until you get down to finding out, how big is the battery compared to what kind of load they're using and what kind of charging they're using. And then you have the whole issue of the charge controllers and all that sort of thing. But there are some other issues in just batteries, and there are lead-acid batteries that are deep cycling, there are lead-acid batteries that are shallow cycling, and you have to approach these strategies differently. And then there's also the issues of nickel-cadmium batteries, want to stay around and be in the market forever. There's a reason for that. It costs you to recycle them. If you have a nickel-cadmium battery right now, and you've decided that it is not of value to you anymore, you have very few options on what to do with that battery. You can't leave it on the, go down to the county dump and leave it there. They won't accept it. You can't take it to a lot of battery shops because they don't want to deal with it either. And there are very few places, in fact, there's only one, EPA licensed recycler in California that will accept nickel-cadmium batteries. Yeah, he'll do flooded cells. And so you have this problem of what do you do with these batteries? Well, there is this market that has appeared of used nickel-cadmium batteries. It is basically a function of government and railroad, big industry, in my opinion, of course, that has found ways to keep these batteries out of disposal sites or out of, actually being recycled. Right now, if you have a battery, it's a nickel-cadmium battery, you can send it to Sab Knife in, I think, South Carolina or North Carolina. And they will accept that battery, but they will accept it in what? 70 cents a pound in under truckload sizes? Plus,
Something like that. They have a sheet that they'll give you all the stipulations and stuff.
plus you got to transport it there. You're not transporting just, a loaf of bread or toilet paper or something like that. It has a different classification when you have some.
This all goes back to don't build it if you can't dispose of it, or don't use it if you can't dispose of it. Right now, just like Rob's saying, lead acid is the accepted technology because of car battery. You can recycle lead acid battery locally, and that's all he was saying. But the NICADs, they've got their pros and they've got their cons. They may have a longer cycle life, but who said they have to cycle in home power use? We've been running our system off of our stationary batteries for 7 years and cycled deep 3 times in the past 7 years. You build your system to accommodate your use. There's no sense in having deep cycle batteries if you don't need deep cycle battery. The deep cycle battery will not last as long as a shallow cycle battery if you put it in a long application and vice versa. But when you put a shallow cycle battery in applications like ours, which the calcium is not very well suited, but it works fine. The pure lead is a decent battery. Actually, it's a superior battery because it's high efficiency, the low self-discharge. You can see what's going on inside the cell as it charges and discharges. So, and plus the fact there's still lead acid and can be recycled. So you got to look at all things considered, and recycling should be a major point.
Okay.
Well, all the battery technologies can be recycled.
Yeah. Maybe to wrap up here, a consensus.
That's another issue.
A consensus of this.
Right.
Batteries don't come with a, you will get 2,000, 1,500 or whatever tag on the side. There's no way that the battery people here can make a battery and guarantee you X number of cycles. We as users have a profound effect on how long that battery lasts and how efficient that battery is. by how we have sized it into the system. Have we sized adequate capacity into the system, or are we working that battery hard every night? We are also responsible in our recharging. Do we have proper regulators? Are they set in the proper positions? If it's a lead acid system, does it get periodic equalization? All of these things contribute to the lifetime, or the how long a battery lasts. And now a lot of this is up to us as users. We make some of the decisions the day we buy the battery, in terms of the technology we buy, in terms of the size that we buy in proportion to our uses, and we make decisions based every day on how we cycle these cells that are going to affect their lifetime. One major difference between the alkaline and the acid technologies is in a lead acid battery, the electrolyte actually participates chemically in the reaction. It actually changes chemical composition. This is why we can use a hydrometer to determine the battery's rough state of charge. In an alkaline technology, the electrolytes do not participate in the chemical reaction. They are merely there as an electron shuffler. They just move electricity one direction or the other. They're there as an ion transfer medium rather than participating in the chemical reaction. So what we're dealing with here are really apples and oranges. These are radically different battery technologies. They need to be specified into systems differently, and they need to be treated by the system's users differently. And if you're not speccing the proper battery in the proper size, installing the proper charge controller, and doing the rest of the minimal maintenance that's required, then you can expect very short life out of any battery technology. So, you know, and we're onto a hot potato here. What is the best battery? What lasts the longest? The question is, we don't know. It's up to you. It's up to how you use it and how you apply it. So let's go for another question here.
Okay, you mentioned about nickel iron. Now, does nickel iron have the same ability to be deep discharged as the normal deep charge, the Trojan at 145 or 105 or better?
Yeah, I'd match the nickel iron cycle capabilities up against any lead acid system. You bet.
Okay, will it last longer? What are the abilities of that to give you power?
Go ahead, John. You do this all the time.
I mean, nickel iron's the proof's in the pudding, so to speak. John Lorenzen in Iowa is when I first got started in the American Windows Energy Association, 20 years ago, as a matter of fact, I was in a meeting in Iowa, and I first read about this character in I think National Observer or something. It was sort of interesting. There was an article. It caught my attention because I just bought my first wind generator, and just got into renewables, and I knew that my wind generator would probably last me 30 years, and I had some experience with lead acids, and I wasn't really that happy with them for various reasons. But anyways, I would start looking and researching batteries that would last longer than maybe 5 or 10 years. I wanted my battery to last as long as my wind generator. So I started doing some research, and then I found this thing called nickel iron battery and a nickel cadmium battery. I sort of heard I know nickel cadmium battery, but I always thought they made them in these little tiny sizes. I never knew they made them in big sizes. So once I liked the fact that the nickel iron was environmentally benign, and so I started pursuing that angle. And lo and behold, I found all these used nickel iron batteries, and so at that time, I had to deal with 120 volt DC system. At that time, was 12 and 24 volts wasn't there just weren't many inverters around, so on and so forth. But at any rate, when I went out to Iowa, he invited everybody from the conference to go to his farm to see his setup. So I was sort of thrilled to go, and that was my first time I laid my eyes on a nickel iron battery. And just recently, I always wanted, when you have a nickel iron battery, when they made them, okay, they put a serial number on all the cells that they made. These are the original ones made by Thomas Edison's company. What they did is they put a serial number on them. They have three different things on the top of the cells: a serial number, a 2-letter code or 1-letter code, and another model. A letter and a number, which indicates the model, which indicates the amp hour capacity of that particular cell. And anyways, So when you get a nickel iron battery, if you have a dealer gave me a card code, okay, that he gave me the code, the date code basically. If it was stamped, let's say YY on the top, then that battery is manufactured in, let's say, 1949, okay? So I knew that John Lorenzen had these batteries for some time, and I sort of wanted to go over there someday and get the numbers off the top of these batteries. And so...
Get to the point, huh? Come on, get to the point.
So anyways, a friend of mine did go and get some of the numbers off the top of the cells. I mean, some of the letters off the top of the cells, and some of those batteries are 60 years old.
Could they be used in an EV?
Yes, they can. We have sold, not a lot, we've sold one set so far.
Chrysler's putting them in their EVs.
Yep.
Why don't we start producing them then? It would be cheaper.
Eagle Pitcher is making nickel iron batteries brand new for Chrysler, but at this point they aren't in production. They're just in limited production. They're planning a plant, I believe, in, I keep hearing 19 this, 19 that, but they are apparently planning on gearing up to do like 100,000 a year or so, but we'll see.
So, nickel ions, it sounds wonderful, and I think a question you've got to ask is, well, why did nickel-ion batteries go out of production totally in this country, and why aren't we just using them for everything? And the reason is that they do have some downsides, and I think there are three. I'll say the ups again, Mark. They're environmentally benign, they're relatively inexpensive apart from the nickel content, and they're very long-lived. The downsides are they tend to have higher internal impedance, which means if you want to use them with an inverter or an electric vehicle, you might have trouble in doing peak loads or starting off from the lights. They tend to be far less efficient than other battery technologies, lead acid and nickel cadmium, perhaps in the sort of 70% range rather than the 80% or 85 or 90 you can get with some of the other technologies, which means if you're putting them in an alternative energy system, if it's PV, you're going to be needing a lot more photovoltaics on your roof to get your nighttime load satisfied. If you've got a lot of excess power, such as a wind or a hydro system, then they can be an ideal battery. The third thing is that to fully recharge a nickel-ion battery, when you get part way up, you start getting gassing at the ion electrode. You get, I think it's oxygen involved there. And to get the battery fully charged, you have to do a fair amount of electrolysis in the battery, which results in two things. One is that lower efficiency, and the second thing is you end up with a higher maintenance. And you also end up with hydrogen production. And I think in the 80s, when electric vehicles were being researched, that scared a lot of people off the nickel-ion possibilities. Hoppinger, this whole battery technology started with nickel-ion at the Volkswagen Mercedes research labs in the late 70s. They moved to nickel-cadmium because they were worried about hydrogen evolution in the batteries. If someone's charging their car in the garage in an enclosed space, they were worried about the maintenance issue of watering. And one last point aside from this on EV batteries, I think to get EV batteries for the masses, we need either automatic watering systems or better sealed recombinant batteries that don't need maintenance. You can't expect the average person driving their EV to work every day to once a week or once a month take off all of the caps and top them up.
Well, I think again, the infrastructure is going to solve a lot of that problem, but that's totally a philosophical discussion at this point. Let me point out a few things, and we'll get right to you, okay? Fredonia Group is an independent research company that does studies on batteries in different markets, okay? And their 1991 report indicates that the total battery market was $6 billion. Okay, that includes secondary rechargeable batteries or primary batteries, which are like flashlight batteries, okay? Of that, lead-acid batteries owns 55% of that market. Nickel-cadmium owns 5%. If the technology and the cycle life characteristics are so much greater than lead-acid, why don't they have more share of the market? But that's not the point here today. The point here today is to hear what you have to want to know about the battery systems. So let's stop trying to sell these people batteries, and let's hear from the battery.
That's a very good point, Jim. There is no ideal battery for your system. There may be one that's better than another, but this is very individualized. So if you have specific questions, you're not going to find out from us what is the ultimate battery here today. This won't be solved here. We'll be fighting about it years from now, as we have been 4 years. So let's just go ahead, yes.
Question, the day I learned you never put water in a factory when it's low, please explain why.
Me?
Doesn't make any difference. The same with the
Well, for a
program.
lead acid battery, the reason is that because when they talked about the acid being part of the reaction, it's like taking ice cubes out of the water. And when the acid goes into the plates, the water level naturally drops. So if you water first and then recharge, it's like putting ice cubes back in the water, and it actually overspills. So the first thing you want to do is charge your batteries and then water them to avoid any spillage or any mess that you might have to clean up.
Make sure that the water covers the plates, that's the minimum.
And we're talking distilled water here. Don't ever add anything else to your batteries, not river water, creek water, rainwater, soda water.
If it depends, you could use Budweiser.
You may like it, but your battery's not going.
They're your batteries, you can do whatever you want.
Go ahead, go ahead.
Drawback when batteries are being charged under high current to be adding water to the batteries.
When they're being charged, I don't know.
Charged under high current, you add water during the charging cycle. You must be lowering the internal impedance of the batteries, which cause problems.
Well, the only time that I would add water under high current charging is if I start to notice that the plates are going to be exposed. That's the only time. Generally, you can charge, because during high rate charging you get what's known as gassing, where it's an electrolysis process. But anyway, that also displaces the electrolyte and raises the level. So you really don't need to water the batteries.
People will say, well, I want to water the batteries while they're gassing, and the gas is evolving to mix the electrolyte.
The electrolyte's already mixed if it's at such a point that you have to add water to it. It's already mixed. You can water it, but it's just as easy to take the charge off and water the battery. Safer, actually, to take the
That's
charge
what I was
off.
wondering, if there are other problems other than safety related.
I want to hear this guy's question, he's got his hand up.
I do too.
What if you do need, say, an 80% depth discharge, and your cycle time is 1 hour? What's available now?
Well, let me get my spec sheet out.
You're looking at some pretty rugged service on a battery there. Discharging it in an hour is very rugged
To
service.
do it, it's going to cost you batteries.
Yeah. We have a battery that's rated for that. It's used typically for starting diesel engines, starting aircraft. If you flew here, there's a fair chance that the battery you used was either a sintered plate NiCad or a fiber NiCad made by Lockheed or one of the subsidiaries in the US.
And I'm saying like 12 volts, 20 amp hours.
Yeah.
20 amps to 1 amp.
Yeah, very possible.
I'd recommend an aircraft sintered plate nickel cadmium battery for that application. It's got incredibly low impedance. That's what they're designed to do.
We can do that.
How about lead acid?
I would recommend, is this for a home power application? Excuse me? A lawnmower? Well, let me answer that, because we're working with a lawnmower manufacturer in Southern California who claims that he'll be moving 150,000 lead acid batteries this year, because that's the battery of choice. So he's using a DC22F, which is a deep cycle automotive type format battery. Okay? No problem.
I'll pick up one of these after two and have a look at the specs.
You know, I hear a lot of conflicting stories, because everybody I talk to when I bought my lead calcium batteries, there are lead acid, but they are also calcium, said, oh, it won't work. And here's the problem. When you go out and buy all these modules to run the house, you go buy the inverter, you buy the tracker, you buy the Amanda Power Source Center, pretty soon, there's no money left. You can't buy that nickel cadmium battery. So I go and buy these
We
batteries.
finance.
I went and bought these batteries, and everybody says, oh, you're going to have nothing but trouble.
And what's your experience been? Have they given you trouble?
They're terrific. But
There
see,
you
so
go.
I'm asking, what's all the misinformation?
It is not misinformation. You've heard probably the parable of the blind men and the elephant. Okay, this is what we're dealing with here. All of our systems are different. All of our usages are different. It's no wonder we're getting different experiences with these cells.
Just like stereo equipment. Some guy likes one manufacturer, some guy likes somebody else.
What do you say the safe discharge rate is of a lead calcium battery? And I know that there is a difference there, but it's not
that critical of, like what you guys said, it's just oversized.
Are you talking lead calcium now?
Yeah.
I think somebody pointed out, one of the gentlemen here at the table pointed out that lead calcium, first of all, and it's no secret in the battery business, is not a deep cycle battery. It's a standby power battery. It's a battery that bridges the gap from the time the power goes out to the time the generator kicks on. 30-second discharges up to a minute, okay? Once every 6 months, okay? So you can't compare lead calcium, either wet or sealed battery, to nickel metal. Nickel cadmium metal. Okay, well, I used to work for a lead calcium battery manufacturer.
I can maybe cast a little light on this controversy. Back in the 80s when I started in TVs, Arco Solar went to a big battery company, which was Delco, and they said, we'd like you to pick out the best battery to match with our photovoltaic modules. And they said, we have just the deal for you. And here it is, and it's the Delco 2000 oil stick solar on the side for you, and it's a lead calcium battery. And then you read the fine print and it says, don't discharge this battery below 15% or you'll blow your warranty and all that sort of stuff. A typical PV system designed for 3 days of storage, which is about what you need typically, would go on average, say, to 30%, right? So you've got a necessarily oversized lead calcium system. If you do the simple sums of looking at Trojan or a quality deep cycle battery, and you look at the cost of the batteries and you divide by the number of ampere hours you put through, so you end up with cents per ampere hour cycle or cents per kilowatt hour cycle, you'll find that deep cycle batteries are a far better choice than shallow cycle batteries. You can do it, but if you go below 15%, you're going to...
So wrong.
Let me just add one more thing. We used to manufacture calcium forklift batteries. I mean, the quintessential deep cycle application, okay? Every one of them got recalled. Okay, calcium is not a deep cycle product. If somebody's trying to sell you a calcium battery, tell them you need to shop.
15%.
Okay?
Wrong.
15,
Yeah.
20.
What kind of batteries you want?
You got, I think they're lead calcium, I'm not sure.
Okay,
But
so it says they're 1.2% acid. So see, here's my...
1.215. Yeah. Specific gravity. Okay, there again, we're going on.
Different systems,
Yeah.
different
yeah.
sizes.
You have a 1680 amp, well, the one we just gave you was 510, turned out to 1180. Okay, that is oversized enough due to your shallow cycle for your lead calcium. You'll find that your lead calcium battery will use less water than lead antimony. You won't have to be as careful. Well, you still have to observe it's still a lead acid battery. You can't neglect it. You can't walk away from it in a discharged state. But any responsible operator of any household wouldn't do that anyway. If you consider we got to buy a battery. So your battery is going to operate just fine for years to come as the many lead calciums and lead antimony stationary batteries that we've sold for years. Now, the only reason that for a while I was leaning toward lead calcium in our applications because of less water usage and less maintenance, basically. Okay, now we've gone to basically the pure lead, which uses even less water and has even less maintenance. No hydrometers are even required for that. Now, I'm not trying to sell batteries.
Questions, applications.
Just like to add one more thing to that. Lead calcium batteries, if they're sized properly for your system, and you're using them less than 10 to 15% depth of discharge, and you add water to them, they're probably going to work just fine for your system. In the Doppler 2000s, their major failure mode on those batteries, they were sealed batteries. You could not add water to them, and they were overcharged because they didn't understand how to charge the damn things in the system. Okay? You could have got in there and added water to those batteries. You could have had the right charging method, and they were sized enough so that they weren't discharged greater than 10 to 15%. They would have been fine. Okay? So you don't have a bad battery. You have a battery, if you use it in the proper application, it's going to work very well for you. Same thing everyone else is saying here. If you use it properly, it's designed, sized right, it'll work okay.
I don't believe I do have a bad battery.
Whether you philosophically want pure lead or lead calcium or antimony or NiCad, it's debatable.
Now, philosophically, we don't want anything. We want electricity.
Yeah.
We'd like it at the cheapest cost for as long as possible.
But I know that everybody's got their hand, but I just want to finish up what I'm saying. The main thing for me is I feel what really sold me the batteries was when Steve Wiley told me that, listen, I use these batteries 20 years there. Now, how much more testimonial do you have to have than that? I got the batteries, I went for 14 days, nothing but storms, you know, threw off those batteries were perfectly fine, and have had no trouble. Everybody that has bought the same battery as me is thrilled to death. So I think if you bought that to try to run a train, like what he said, or take so much out of it so fast, I think there's problems. But I think if you can design that for your system, I think the battery is totally the right battery. Otherwise, the telephone communications would have never applied that to that.
Well, so maybe the first point here is your battery experiences are determined by how well you specify that battery right up front, before you even buy it. That determines a lot of what kind of experience you're going to have in service after that. And it's a good reason to do your homework before you buy a battery. And if you don't feel like doing the homework, then pay somebody who's already done it to do it for you. Okay, let's go again. This gentleman.
I have telephone batteries, got 24 of them. You know, you put 6 of them in to get 12 volts. 2 years ago, we went down to 28, and out of each bank, the plastic split. So I had to revamp my whole system and pull these 2 batteries out, which made me lose 1/4 of my whole system. Now, can these 2 batteries be fixed?
Split, you mean the top's cracked?
It just split all the way down.
All the way down? So it's history.
The plates have grown beyond the capacity of the job.
No, they look real good.
That's why the case cracked.
Sounds like they froze. They froze?
Yeah, I guess it goes. One night, 28.
It's history.
But the others were beautiful. But now I lost 1/4 of my system.
They're ones on the edges, they
No,
outside.
they're right in the center.
You need an accurate battery. They don't freeze. What was the temperature when they failed?
About 28.
What was your state of charge?
Plates are in the case cracked. They're in the middle of the thing, it didn't freeze.
Yeah, but when the plate, see, a lot of people think the plates look just fine when they're not really just fine, because you have to know what you're looking for to look at battery plates. You know, being the telephone cell in the clear plastic case, you can see what's going on inside that cell. Okay, they may look just like when you bought them, but when you bought them, they might have been as bad as your fist, and you wouldn't have known the difference from the day they were built. The lead-acid battery plates grow and separate as they age. So I think that's what happened, is your batteries or your cells outgrew their container. Because at 28 degrees, I don't think, you could almost have them dead and then not freeze.
I don't know what the others didn't do that, and they haven't done it.
Look at the draw batteries are very different. The factories that they're made of, it's pretty, you know, the plates, the pasting of those plates is not the most scientific.
The other part too is that you don't know if it's a jar material, molding problem. I mean, there's any number of explanations.
They could have shifted. Do you have solid bar interconnects or flexible cables?
No, but I got it. They're all on. They can't move.
Yeah, but the cables from post to post, are they cables or are they?
Or they cable? They are cables.
Yes.
And if it had been solid bar interconnects, that could have been what caused it.
Mechanically have to
Right,
work the
that could
cells.
have been, right.
Let me ask a few questions from this way to that way. How many of you have batteries that if you experienced an earthquake, they wouldn't move? Not the picture in your magazine.
Oh, it didn't have the safety bars. I put them in after Arcata. I watched Dave Katz trying to keep these batteries from falling off of a picnic table. I learned that.
How many of you have fuses in your battery system? How many are going to have fuses in your battery system?
That's interesting, that's 50%.
Here's a good question. How many people here live on batteries? Whoa, we got a live crowd here.
A follow-up on the quality of batteries, because you said it's a luck of the draw, so to speak. It's not very scientific. There's no consumer reports to help a new battery buyer decide whether, if you decide on lead-acid deep cycle battery, whether you go chloride or Trojan or IBE or whatever. How does one shop around?
Look at your pocket.
Good question. I can answer part of that question, and that is the reason that there's no consumer reports is because now that the market is growing in photovoltaics and solar and electric vehicles, batteries, or lead acid batteries in particular, and I'm sure the nickel cadmiums as well, and the industrial sizes are going from a predominantly industrial type piece of equipment to a consumer product. Okay. And that's the whole purpose of this deal, is to educate the masses onto what to look for. You know, we're here to help you make some kind of educated decision.
And we want to also provide the information that you need so that you can match your expectations with what you buy, and that performs the way you want it to perform. And so it's an education thing that's going both ways, so we can give you the right kind of information, and you can ask the right questions because you know what they're
The kind of education.
Consumer-based industry for a long time. It's been industrial-based, and so the decisions were made differently. Now that it's becoming consumer-based, if we keep telling the battery manufacturers we want this information, they will come up with it.
But right now, the only information is from the manufacturers. I mean, and they say it's so many amp hours and so many, volts.
I would go to an end user.
I'm sorry.
I would ask an end user.
Okay.
Yeah, but that changes just as much as...
Yeah, you guys.
We have 500 different opinions.
If you decided that you wanted a float-type battery application, which means you got a big battery for how much power you use, then you can go around and ask people, I want a big battery that I'm not going to use very much of. Which ones do you like? But if you say, I want a battery that's going to take care of my house, you have to get more specific. You have to say, do I want a big battery that's going to float? I'm going to use just a little bit of it. Do I have a lot of dollars, or am I going to buy a recycled product at a discounted rate? And if you don't want to do that, then you say, okay, I want a battery that's going to cycle a lot. Then you go and find out about batteries that cycle.
Well,
You have to design your system, and this is where your local dealer is going to come in. Because generally, the dealers nowadays are already users. They
Almost
know
without exception.
what their systems do.
I think specifically to the question, testing batteries is not an easy business. You can set up something to do it. If you've got a sizable alternative energy battery and you're going to run it at the same sorts of rates that we run batteries at, you're going to have to test it over 10 years, right?
6 years.
And so you've got to put a lot of money into it. You've got to pump a lot of energy in and out of a battery. And for someone who's off-grid like this, that's a hard job too. And it's just something that you can't take on lightly. It's a difficult thing. Perhaps someday we'll have the Solar Energy Industries Association have a testing lab that could do it independently.
I'd just like to second the point that one of your best sources of information is your local dealer or distributor. He's been in business for 5 or 10 years. He knows what works and what doesn't work.
Yeah,
He doesn't want to go out and replace batteries. So it is a
And
good
if he
source.
gets a bigger big off the lead acid, he'll sell you lead acid. If he gets a bigger big on
I would disagree with you there. The solar dealers have been out there long enough that they know that the quick buck comes back and bites them in the butt. So these folks are in it for the long haul. They want you to be a satisfied
You
customer.
still can't go wrong. You got a nickel cadmium on one hand and you got lead acid on the other. I can show you either one, and either one's going to work.
Either one's going to work, either one's going to have good points and bad points, differences in cost and performance.
So whatever he pulls out of his pocket, makes
Yeah, okay, pardon me. All right, we're giving this one the hook. On to the next one. Who said we got questions out here?
I did, but I don't have one.
Oh. Okay. Let's try the gentleman in the green t-shirt here.
The question I got is all these guys, we've been listening here to these guys talking about nickel hydride, cadmium, lead acid, and all the rest of it. Like, when I first got my solar power system, I live in an area where there is nobody else that has a solar power system. And you go and you visit some guy who's got a homemade system, and you like what you see, and you know it's the wave of the future, and you want to get into it, but the information just isn't there. Everybody's pushing nickel hydride, that's the best. Lead acid, that's the way to go. Deep cycle, that's the way. Shallow. I mean, this is all foreign to the ordinary, everyday guy. And everybody's pushing, I got so many amp hours of acid. a discharge rate of speed 20 and whatever else. The question I got is, why in the hell when they put out information on how to maintain the batteries, what the batteries can do under the maintenance conditions you're using, like these guys are saying, 15% cycle, 20% cycle, 80% cycle. The guy buys telephone batteries, how the hell do you treat them?
Buy
None of these things even come with maintenance.
Power magazine.
And then they sit there and say, well, size your system for what you want. Know what
Okay.
battery you want.
Hang on, I'm giving you the hook. I understand your question is, why don't we publish information about how to use these batteries? I've got to say is, has your home power subscription lapsed or what?
Power subscription that started on number 14.
All right.
Okay? And it wasn't until I got home power number 14 that I even understood there was such technology out there.
Right.
The point I'm making is there's 300 million people out there that don't subscribe to home power.
I know.
And they don't. And the manufacturers, these people sitting out here that sell the batteries, they don't give you that information.
Oh, wait a minute.
I got to
Wait
respond
a minute.
to some of this.
If you have a question from somebody who's planning on purchasing your, hang on, John, on your batteries, if they call you up on the phone, I can't believe there's not one person sitting up here who won't bury you in information.
That's precisely the point. They'll bury you in information on how well their product works. But they will not bury you. That's a good one. Bury you in information on what specifically their product does and how you want to use it.
Well,
I've got a whole system I have questions about now because you brought up new questions I hadn't even thought of. So where's the information to help me with that?
Okay, I've got a response to that, okay? My name's Steve Harrington again, and I work with San Diego National Laboratories. National Laboratories are funded by your tax dollars, okay? The first thing to do is you call the National Laboratories and ask for some information or a resource for it. If you don't feel there's enough information being put out on batteries, talk to your congressman and ask why aren't the National Laboratories providing some information on batteries? Especially for the electric vehicle. Now there are other products that we do work with, okay? We have tried to put out a maintenance and operation manual for photovoltaic systems. This document is free to you, no charge. There's information if I haven't gotten to you at this conference, you can get to me either through Keith Rutledge or Home Power, etc. Okay, this is just one of the documents. We are working as far as consumer information on how to use lead-acid batteries and photovoltaics. There hasn't been this big push until not too long ago when the market really opened up for small standalone applications, lights, etc., using small, 100 amp hour, 200 amp hour batteries, the Delco 2000s, etc., the T105s. As we started to test these batteries and have more information about them and had more interaction at the solar conferences between the research industry, the battery industry, etc., we're preparing some information to build application notes for batteries and photovoltaic systems. Like you buy an electronic gizmo, you get an application note. Well, we've been polling the industry and trying to we need to tell the battery manufacturers what's in it for them. We need to tell them how much of a market it is in there so they can spend the money to test these batteries. We need to tell them exactly what we want. We can't just sit here and say we want information. I really don't understand our business. We need to tell them exactly what it is. For that information, I'm looking for people who do small standalone systems, etc., that I've got a survey. I need to know how these systems are used so that I can take this information and put it in application notes. We've got a group that we formed at the last Soltech meeting, which is a meeting of industry people, that will review this information. It's not just me sitting up in some place coming up with this information. It's reviewed by peers. We're going to the battery industry. They've been very receptive in the last year about doing this. Stuff does take time, but we can have it. Okay? But we have to get involved. We have to tell them exactly what we want and what we need. Okay? And that information is coming. Within the next year or two, you'll see that type of information distributed by not the national laboratories, not a magazine, but the source of the product, the battery manufacturers will endorse this information for PVUs.
okay, and where does the information come from? It comes from out there.
You come to us and tell us.
That's right. Let us know what you've been doing and how well it's been working or how well it's not been working.
You have an 800 number?
You have an 800 number, an address.
Okay, let's try to take a question from Larry here.
There will be more information to follow.
You can write it up there.
Sarah,
Yeah.
I put it on board.
Go ahead.
I occasionally design small standalone systems, and I try to design them to last a long time and work well. One of the problems is, like buying batteries, we don't know how to set the charge controller. If you call up the battery manufacturer, they don't understand solar charging generally.
It depends on the phase of the building, whatever.
And they say to call up the charge control manufacturers, and then the charge control manufacturers see the battery, and you can't get good information. One of the things is, like when you say depth of discharge, you might go from a fully charged battery to a 50% charged battery over 3 weeks. How does that compare to doing charging and discharging cycles? It's different in solar applications. And I think there's been very little research done, probably because the battery manufacturers feel like there's not enough market out there to spend any money trying to think about how batteries are affected in solar applications.
I had a great presentation here, but then again, because we're here for your questions, we needed to hear that. We have been doing a lot of research on the different types of, all the different charge controllers out there, because this is America. We've got entrepreneurs out there who have all got a better mousetrap, okay? We've got a lot of different charge controllers out there that charge batteries in a lot of different ways. We've spent the last 2 years, we've been trying to, it takes time. I mean, this is even just 200 amp hour batteries or 100 amp hour batteries. If you want to look at 2,000 amp hour batteries, you're talking about, it takes much longer to find out what the effects are. So we started on the small batteries. Done a lot of research and reports on this information on how, what the set points on, etc. We're taking that information, going to the battery manufacturers, saying, okay, this is what we found out. Okay, I need you to do some testing to concur with this and not publish information that says this is how we should charge the batteries. There is information in here in this book about how different charge controllers work. This is when you buy a controller, buyer beware, consumer must understand what he's buying. Ask the manufacturer, how does my charge controller work? Okay, does it go on, off, or whatever, you know? And how do I set it if he doesn't know? They won't tell you how to set it. Well, they tell you how to work it, okay? All I can do is provide some of this information. In the future, this information
Yeah, if they tell you how to work it, how to work it, not set it, then obviously it's non-adjustable. It's that simple.
Okay, with lead acid battery charge controllers, sorry, yeah. I think there's a fundamental problem, I hope Stephen will agree with me here. With lead acid battery charge controllers, you've really got two conflicting problems in what the charge controller's got to do. And that's the reason for all this problem over the years. One is, if you don't fully charge your lead acid battery, say once a month it's going to sulfate, and it's going to wipe out that amount of capacity. The other thing is, if you overcharge it, you're going to end up with water loss, electrolyte going down, and you're also going to perhaps erode the plates and wipe out the life of the battery. And so the simplistic charge controllers we've had to this point, I think, try and balance that in various ways, generally by having 2 voltage set points. Some of them go up to a place, then they turn off or cut down the charge, and when the voltage drops to another place, they turn back on again. And I think one of the problems there is that it doesn't really satisfy all the needs of what you do with a lead acid battery. In the commercial sphere, people generally don't do that sort of control. They quickly fully charge the battery and they bring it to float, and that whole system's really been optimized over a long time. So I think one of the real problems is that our charge controllers really are too dumb at this point. And speaking to that, I've got a product that's not out there. Smart charge controller.
I thought your specialty was
I'd like to...
Let's let me finish, then you're on.
Okay.
I think separating the two functions of getting over the sulfation problem and also making sure you don't keep the battery at so high a place that you're doing electrolysis and losing electrolyte or eroding the plates solves that problem. And this sort of charge controller has a time clock in it that says once a week I'll equalize the batteries and the rest of the time I'll run at a different place. And it's also a maximum power contract. So it's not on the market yet, but maybe by the end of the year you'll see it.
It sounds that has a lot of the flavors that you need to make a good charge controller. But I can't really go into that unless you're going to listen to the whole thing. I don't want to give you bits and pieces. At the end of this meeting, if people want to hang around, I'll be willing to present my information and hang around late, okay?
Fine. We conceive of this session as a question and answer, give and take, rather than us standing up here and running our mouths. Any of us could do it all afternoon for you, but what we want to do is find out what problems you've been having, what questions you have specifically about operation. This gentleman's had his hand up 5 times.
Yes, alkaline batteries, I've had a set of NiCad batteries now for 2 years, and I've had several problems. One is with shorted cells, and another one is with one cell out of a string of 10 losing capacity and perhaps having only maybe 30% of the capacity of the other cells. And I wonder what's causing this, what can I do to prevent it or to reverse it?
Were these brand new cells?
No, reconditioned SAP knife MDP 130s.
And where did you purchase them?
From a company that is no longer in business.
Who didn't have a clue on how to capacity test them from the first place?
Are they centered better? Are they centered plate?
Plate, Pacific West Supply, I assume, is no longer.
Okay, I can answer. When did you buy them? 4 years ago, you said? 3, 2?
No, I had one set. They were replaced almost exactly a year ago with another set, and I'm having problems with the new set, which is a year old.
Okay. Reconditioning of batteries, John does it. He can tell you that it's a process fraught with pitfalls. In the beginning, when Pacific West Supply was recycling batteries, they called up SAP Knife in North Carolina and said, "How do we do this?" And they said, "Oh, you just pour the old electrolyte out, put some new stuff in." And what we found out was, Knife does not recommend removing the carbon residue at the bottom of the cells. This carbon residue, if you don't get it out, 1.5 years, 2 years in the line, into service, you have carbonated electrolyte once again from the graphite moderator packing, which is used. So what we're doing here is we're still learning about doing this.
Now, these later cells were purchased after, actually were replaced after
the clean out.
Right, after they decided to do it that way.
And you've maintained your oil layers?
Yes.
What's your ambient operating temperature?
About 70 degrees.
About 70 degrees, so overheating is not a problem? Are they full every day?
Just about every day.
Are you sure you're not overcharging?
I never get them above 15.5 volts.
One of the fastest way, that doesn't sound overcharged to me. One of the fastest way I know of carbonating electrolyte on these pocket plates is chronic overcharging. That'll do it in a very short period.
Why would one cell?
No, one cell, it would be all of them, or majority.
Do you have a low voltage cutout on your system? Do you have anything like a lights or a well pump that can bring it down to 0?
No, never goes down to 0. All the cells, the lowest I've ever recorded them is about 11.2 volts. And right now, all the cells, 9 of the cells will go down to 1.2 volts. The other one will go down to 0. And I wonder why.
One failure mode that I've seen in selling the private NiCads is people that don't have a low voltage cutout will end up bringing their total battery terminal voltage to 0. And that means that some cells will be reversed and some won't. And then when you recharge out of that, the ones that are reversed take more charge than the ones that weren't to get them up doing anything. And they get worse and worse. And the bank just gets out of balance. It doesn't harm them. But that's something that happens quite often with people who don't have a cutout. It's not good.
You say you charge at 1.5 volts per cell on a regular basis? Is that your limit? I mean, is that what your charge control set at?
Right, but I have lots of modules, and I have in that 130 amp hour pack, I have up to 30 amps charging.
Well, what I would do is I'd put your voltage up to 1.6 volts per cell. If you're whatever else you have, bother that, and cycle them once or twice. See if they come back.
In other words, you may not be getting them totally full, not 1.5 volts per cell.
Say cycle once or twice.
In other words, when I say cycle, that means take it down to 10 volts.
Pacific West Supply didn't sort out the good ones from the bad ones.
What an idea. That was the case in a lot of these batteries.
How do you handle the disposal of the electrolyte if you have to dump it out and refill it? I mean, that's what
It goes back to an authorized nickel-cadmium dealer, somebody like John. Don't dump it in the landfill. Make sure that it's disposed of. nickel cadmium electrolyte contains a minute amount of cadmium. We don't need any of it running around in the environment.
So now this is generally I don't know, some semblance of a maintenance procedure that has to be done.
It can be happening.
Not quite unlike having the water.
No, it can happen in 2 years. It can happen in 15 years. It depends on temperature and how the battery is cycled. So once again, we've got questions without answers, and I expected this would happen over and over again. We are not, I mean, these batteries have been around for 200 years, since the days of Alessandro Volta, and we're still finding out things daily about how to use them and apply them. So please bear with us. If we can't answer your questions succinctly, it's because we don't have the foggiest idea. We're still figuring it out. Go ahead, gentleman in the back.
Yeah, I'd like you guys to try to address.
Stand up, please.
If you guys can try to address two related questions. One of them is the function of plate size in a battery bank to the capacity of current it can deliver. I'm specifically thinking of so many home power systems that are using inverters and taking bigger and bigger loads on inverters. And I see one battery bank sitting there with a whole bunch of dynasties, and they say it's 1,000 amp hours. I see another bank sitting next to it that's only 6 cells, not a whole pile of batteries at all, but they're big plates. My intuition is that for running an inverter on large loads, the big plates are going to do a better job. I'd like your comments on that. My second question has to do with battery recommendations in northern or cold climates. Thank you.
Who'd like to handle the plate size versus anybody here with? Okay, Jim?
To answer your question on the plate size, okay, if you have a multitude of batteries connected in parallel, you have to go back to your basic laws of electronics, okay? In series, voltage is additive. In parallel, current is additive, voltage stays the same. So we can parallel a number of 12 volt or 24 volt packs to give us that 1,000 ampere hour. Do you follow me so far?
Yeah.
Okay. Now, in a series circuit, the ampere hour capacity of the battery is the same as that of each individual cell. It's not an additive thing. So if you have a 350 ampere hour L16, for example, the whole battery is 350 ampere hour as long as everything's connected in series. Okay, so that's why you can have a bunch of small batteries that collectively have a rating greater than the battery with the bigger plates. Now, the thing with the battery with the bigger plates is now you have greater surface area and more active material to distribute the current of the load across each plate. The plates are connected inside the battery in a parallel formation, the positives on one side, the negatives on the other. Therefore, if you have a 100 amp draw, each plate, based on the number of positive plates, divides evenly and supports that 100 amp draw. Okay, so the larger the plate, the more ampere hour capacity on a per cell basis, but the more batteries you parallel, the more ampere hours you can ultimately generate.
Yeah, but which one is going to deliver the current that the inverter requires better?
Strictly a matter of surface area.
In surface areas,
well, again, it goes back to this sizing thing. It's going to depend on how deep you want to discharge the battery.
But wait a minute. It's also the rate at which you're doing it. If you're going to run an inverter to watch television, you got a lot different discharge on that battery than if you're running the washing machine.
No, we're talking big loads. We're talking heavy
Machines, things like that.
Then it's the surface area will give you the fastest, response.
And it really doesn't matter whether that surface area is in one big can or in a number of small cans. It's just surface area. But don't confuse, for instance, an automobile battery is made of a lead sponge plates. And why a sponge? To expose maximum surface area to the chemical reaction and still be light in weight. All right, whereas a deep cycle battery like these gentlemen make here, a deep cycle lead acid, has plates of very thick scored sheet lead, usually alloyed with materials like antimony to give it stiffness and long-term deep cycle ability. The batteries are radically different, where a car battery might be able to deliver, a smaller car battery might be able to deliver more amps into that inverter than, say, a larger deep cycle one in terms of weight. But the problem here is not only will it run it, but how long will it run it? So to answer your question, it's primarily a matter of surface area, and it doesn't matter if it's in one big can or in a number of small cans. It's just surface area.
So that means start counting plates per cell and surface area on each cell
okay?
But that's,
Because they will heat and they will warp, and it will cause a lot of trouble.
The small batteries aren't really the answer.
Thin plates are not really the answer. Sponge lead plates are not really the answer, not for renewable energy applications. Rob?
Okay. In the NICAD area, there's a similar question, and it's interesting the way that Mercedes Research Lab came up with a solution on how to make nickel-cadmium or nickel-iron batteries supply the power you need to make an electric vehicle get up and go, was they took a plastic substrate like a Brillo pad, nickel-plated it, and then forced the active material into that. And that's what the FNCs are now. They have an incredibly high surface area of active material that is in contact with the outside world and with electrolyte. And also they don't need a carbon filter, so they don't have that carbonate problem. With respect to low temperature operation, the alkaline batteries shine way over the lead acid. And in particular, again, FNCs do quite a lot better than pocket plate. I've just been designing a system for McMurdo Station, Antarctica, to run the runway inlights on the runway. And it's a very tricky thing. Again, I've spent hours actually getting tests done, working out where the charge controller test points should be and things like that. But in terms of the battery operation, at minus 40 centigrade, which is the same in Fahrenheit, minus 40, we've got about 55% capacity still in batteries, and they'll work fine. And it's probably the only commercial battery on the market that can do that.
Which battery is that?
The Hoppica fiber nickel cadmium.
How cold is what part of the country we're talking about?
We're talking about the other country, Canada, and we're talking regular conditions.
In southern DC maybe, or?
No, we're talking about the Arctic and where.
Yeah, you definitely want to choose an alkaline battery technology for that. See, the problem with lead acid is as you discharge it, the sulfate concentration, the sulfuric acid concentration in the electrolyte decreases. These sulfate ions bond with the plates, and what you're left over with in the electrolyte is water. Water freezes at 32 degrees Fahrenheit. While a fully charged lead acid battery is good probably down to minus 30, minus 40 Fahrenheit, a totally discharged one is going to freeze at freezing point of water, 32 degrees Fahrenheit. So in those applications you need a battery whose electrolyte remains liquid at very low temperatures. And this means an electrolyte which does not change chemical composition with the battery's state of charge. And this is in common with all alkaline systems. This is one of the major stand-ahead type performance increases that you'll get from an alkaline system over an acid system. It's just built into the electrochemistry of the cell. That's the way it works.
But one thing to note is if you want to go below minus 18 Fahrenheit, you've got to use a denser electrolyte. The cells that John works with, the pocket plates and the cell I work with, both require for lower temperatures. I think it's 1.225 specific gravity for the lower temperatures. Otherwise, the electrolyte itself starts to slush and you lose your capacity. It doesn't harm the battery to freeze it. It'll still survive. But
just thaw it out and use it.
You're dealing with extremes there, but you can still, when you buy a lead acid battery, if you're not in that extreme of a temperature problem, you can order these batteries with higher specific gravities electrolyte. But you do pay a price with oxidation in the batteries early, shorten life. But when it's tough, you got a cold temperature application.
Well, we operate.
Options are limited.
We operate lead acid batteries at 20 below zero every winter. It's not for an extended period of time, but there's a lot of common sense things you can do to offset that 20 below zero. If you attach your battery, your lead acid battery, shed, building, whatever, to your building, to your residence, and pump some of the warm air into your battery room, you just solve your low temperature problem.
Well, then you're not running them at low temperature. You're artificially heating.
Well, but we're dealing with overall.
That's right.
Things like putting your batteries in an insulated enclosure using a linear regulator to shunt heat, or some type of regulator to shunt heat into the box. It doesn't take much heat to keep those batteries reasonably warm in a cold environment. So use your excess power that you're not charging in your battery to keep those batteries a little warmer.
I tell people that ask me about battery temperature. I just say any battery, no matter whether it's lead acid or NiCad or whatever, should be operated at room temperature in a home power system.
That's absolutely, you will get longest life and best efficiency out of your cells if you operate them at room temperature regardless of type. This is true.
You can run FNCs to -20 in a home power situation, not have too much problem. We have a lot of people who run in vacation homes in Maine, and I think one of the main considerations there is, especially for folks who have the bucks for 2 houses, they want to make sure that things aren't going to freeze up every winter on them. And so that's a good application.
All right, well, let's go ahead. The lady back there.
Yeah, should we stick these batteries in our house then? I live at 3,500 feet now. I want to put the batteries upstairs, and I want to give it a little bit of vent and put a little box around it.
Bad idea.
Any way that you can get batteries out of your living space, you'll be well ahead. Take it from someone who had a cell explode on his floor. Okay?
The safety stuff is good stuff, huh, Richard?
The safety stuff is essential stuff. You don't? No.
I think something that really hasn't been addressed and should be brought up, something I thought of doing, is actually getting some gas samples from lead-acid battery rooms. Maybe it's something the labs could do for us, and find out the number of houses I've seen with batteries in the basement, a hole through the wall, thinking that the stuff's going to go out there, but because of the chimney effect in the house, the warm air in the house and cold outside, everything gets sucked into the basement, and people are living with battery fumes. I think 2 points there. One is, it'd be really interesting to find out what really is coming out of a gassing battery. It's not just hydrogen. There's
arsine, stubine, lead gases, arsenic compounds, minute amounts.
No, it's just stuff.
Let's keep batteries out of our living space.
Yes.
Let's make that the rule.
No matter what type.
Yeah, it doesn't matter.
And ventilate your battery room.
In northern climates, that's not necessarily a practical solution, but I think there is another solution, and that is, if you're going to have batteries...
Wait a minute.
Just hold on. Let me go first.
You're always going first.
Because I'm bigger than Just, I think a solution, I've done perhaps 50 or 100 systems in northern climates in Vermont, New Hampshire, and people can't practically build a battery house outside and keep it warm enough to keep lead-acid batteries in. Generally, batteries are put in basements, but there is an answer, and that is when the things gas, you use active ventilation, and you keep them in a separate room. And that's a quite a reasonable answer. It's used commercially.
An electric motor, right.
Right. You pump it out.
Perimeter magnet, DC motor.
And you can do that just on
If you're going to use a fan motor, use a brushless motor. Okay?
Yeah, like
The other thing is, the danger isn't always necessary. Yeah, I can give you a formula to calculate how much gas your batteries are gassing. But the danger is between the electrolyte, the top of the electrolyte, and the top of the cap of the battery. Okay? And sparking it like that and it explodes. It's not necessarily filling a room. It takes pretty hard to fill a room with 4% hydrogen.
But always assume that your room is.
But your battery can build 4% hydrogen real easy. But that's what blows up. That's why you see the lids blow off.
Okay, so the consensus here is, don't put them in the house. If you do put them in the house, put an active voltage sensing
Not
switch.
everybody has an ideal solution, that's one
Yeah.
thing.
So to live with it really is use a brushless motor to exhaust the voltage switch.
On a voltage sensing switch. It's a simple circuit. I've got one in my battery room. The next issue of Home Power is going to have the schematic. It's $250 worth of Radio Shack parts and 2 muffin fans.
Why brushless?
Where's your battery room now, Richard?
No sparks.
Outside.
It's run by magnetics and not brushes. Brushes create sparks and sparkle.
Okay, some other things since we're on safety here. We're just going to do this real quick. The door of the battery room should say, no smoking, battery charging area. It should have a sign. The door to the battery room should be locked. Children, watch dad maintaining the batteries. Someday you're not going to be home. They're going to be in there fooling with it. All batteries are electrochemically nasty items. If they weren't, they wouldn't be batteries. And we need to protect all living creatures from what's going on in that room. It could be an explosion. It could be a spill. Inside the door to that battery room, you have rubber gloves, safety goggles, and if you can afford it, a Norex lab coat. You have neutralizing material. If you're a lead-acid person, you have baking soda in there. If you're an alkaline person, then you either have acetic acid or muriatic acid in there to neutralize those spills and deal with them. This is just basic battery safety. If you're running batteries in these systems, then you need to have this safety equipment and you need to know how to use it. And most of all, you need to keep it out of your living area. Make sure it's out of your living area. Don't put it there.
Goggles are a must. If you want to see what happens to eyeballs in a secure gas, I've got a great picture. Goggles, you don't buy the aprons and the gloves and all that crap. Buy some goggles.
Yes, this gentleman.
I'm going to start another series of batteries. Which would be best? To get 6, like the L16s off of Trojan, or a great big one off of somebody?
Far more money it costs, the better it is.
Yeah. Let me tell you. I got some batteries.
All right, we have a question. This gentleman back here.
Well, that's the batteries out of the living area. Walk onto the vehicle, put all the batteries in the passenger compartment.
All right, what about that? What about, Rob, you've got experience with electric vehicles. How can you make them safe? How can we protect ourselves against those
My
batteries?
feeling is that you shouldn't have batteries in the passenger compartment. Many years ago, gasoline cars were made without firewalls. And then someone came up after many deaths with this neat invention, and you know why it's called a firewall. It's to keep the fire outside rather than inside. In my opinion, electric vehicle conversions are pretty tenuous things at the moment if you have to put batteries in the passenger compartment, and if you can't absolutely isolate them so that if that car rolls, you don't get acid on you and so on. And so I think if anyone's considering a conversion at this point, you should look at a pickup so you can keep the batteries out. Hoppinger Battery Company has been involved a lot in electric vehicle battery development, and they could have been selling their vented cells to the EV market as it exists at the moment in this country, and they decided not to because they thought that it exposed them to too much liability, and also they didn't want to give people the maintenance problem of having to top them up. So their opinion is that the only appropriate electric vehicles are sealed recombinant cells. And going back to the previous issue, I'd say in the next 5 to 10 years, because of the electric vehicle industry, we're probably going to see a new crop of batteries coming out that are either fully sealed recombinant cells or something like the lead-acid valve regulated recombinant cells we're seeing now that will be suitable for home use and could in fact be used in a home environment because they're totally sealed. Something to look forward to.
I didn't get an answer to my question.
I've got some information later that's a tough question to answer, okay, without sitting down and making a design, but I've got some lists of questions that if you go through and ask all these questions, we'll have your answer.
Great. That's the third time I heard that question now. So that guy up there that was standing up front, his question never got answered about what kind of battery should he get. Actually, that's kind of what he was on the same line. What kind of question?
I could ask you what kind of car I should buy. What kind of car should I buy?
Okay, well, how many people know what C20 means in here?
How many people know what C20 means? This is not an unsophisticated audience. They've been doing their homework.
C20 means that's the maximum discharge and charge rate you can take, kind of basis on what you can take out of the battery.
No, it doesn't. It means that the battery is either emptied or filled in a 20-hour period.
That's exactly what I said.
But you can take it out in any way you want.
Yeah, you can.
But it's not the maximum rate.
It's not the maximum or the minimum.
That's what the battery is designed to work at.
No, that's just what they rate them at.
That's just what...
No, that's just a test
Whoa, calm down here.
You go to PVC, so you're going to design it. And this guy up here asked the question whether you should get big batteries or little batteries. He needs to sit down, like you said once before, and do his homework and find out what he's going to do inside of his battery system. And I say the same thing to you. Do your homework. And then when you find out what size battery you need, go ahead.
All right, so the question is basically, should I buy one big cell or many little cells?
Or 6 big cells or a bunch of little babies.
Okay, my personal preference is I go for the smaller cells. Why? Because cells, you don't use one lead-acid cell, you use 6 of them in series. Physics tells us it's like a chain, only as strong as its weakest link. You lose one of those cells, the other 5 are out of the action. If you put your money into big cells and one of them goes bad, you're losing a greater proportion of your battery than if you put it in smaller cells. So from that viewpoint, there's one way of looking at it.
No, but there's a big
There are other ways of looking at it. turn into a mob scene and we can't hear anybody, then we're out.
On the other hand, the more small cells, the better chance for cell failure.
More bad connections.
Yeah.
You got to determine whether, first of all, whether you got the pocketbook for a big battery or a small battery. That's one thing to think about, because if you are going to use, 100 amps a day or whatever it is, and you've got a 1,000 amp hour battery, and you can figure out a way to charge it, but you're only going to use 100 amps out, and you can have a big battery.
That's 20 years for it, yeah.
And if you buy a big battery that's a used telephone battery or whatever like that,
The D8, one cell goes bad.
Can you move it?
Problem.
The next question is, are you going to move it? How are you going to get it?
Yeah, that's a good
You're going to
question.
transport that sucker, It's easy.
How about cleaning the flat battery?
Okay. All right.
But back to the one thing about the small batteries and having a lot of them. There's a person came to me and said, well, I got a 1,400 amp hour battery. Well, how many things do you have there? Well, I got 1,100 amp hour gel cell batteries.
In series?
No, parallel. You went to 12 volt, This battery, I don't believe, could ever be charged properly. If it had a chance, it would have equal resistance wiring to each one of those terminations, but that wasn't how it was wired. Of course, it was wired here, the first battery, and then those jumpers all the way down, 14 feet away. And then you've got all those connections happening, and you're not going to have the same potential across each one of those batteries. And gel cell batteries are very susceptible to overcharging and gassing, and once you've gassed it, then you've fried that battery. So that is not an answer.
Well, once you overgas, once you dry it up, it's
Let's move ahead here. Rick.
I've been hearing a lot of really good and interesting questions, and I'd like to just talk about 3 or 4 of them, if you don't mind for a minute.
Okay.
I'm with a company called Cruising Equipment, and we've been designing deep cycle systems for Marines for 10 years. And as such, we see a lot of cycles, we see a lot of float service, we see high charge rates, we see low charge rates. And so I formed some pretty clear opinions about how to build systems in general. And we carry batteries from 8 different manufacturers. And the reason is because there's a right battery for every job. And you need to work with professionals that know and can help you select the right battery. That's number 1. It's got to be sized right. Everybody already knows that. The homework is saying what you want to run. That's what you have control over. Once you make the commitment to turn on the switch, you made the commitment to the batteries, you made the commitment to the PV, you made the commitment to the whole system. Okay? So the thing you have control over is your load list. You've got to make it. You make the load list, the guy can tell you what size to size your batteries. Once you know that, you have to charge them right. If the charge controllers aren't set according to what battery manufacturers want, the batteries won't last. The first way, I bet several, just give me just another 2 or 3 minutes, okay?
That's right.
If you don't mind, if anybody's disagreeing with me really bad, they can throw stuff at me, right? No. So,
you're doing well. You're doing good.
Okay, so I have 3 or 4 things I thought of. This has been a rather long discussion. There's 2 things that kill batteries: overcharge and undercharge. Overcharge is protected by the charge controller. Undercharge is protected with instrumentation. And I haven't heard that mentioned. You've got to know what's going on in the system to be able to analyze whether it's performing properly. So that's got to be a part of it. Once you get all of these things all stacked up, the systems will work. Now, one question here, the big battery, little battery, I want to address that for just 1 minute. We see more parallel battery systems than any place else in Marine because a lot of times vertical space is at a premium. And so it's not uncommon to see lots of batteries in parallel. In 10 years of field experience, I've seen more failures in parallel batteries than any other. I'm not an advocate of large parallel systems. However, sometimes you have to make that decision because of space and weight considerations. Again, somebody that's knowledgeable can help you make those decisions. That's my whole pitch, and thanks, Richard.
There are some good ways to parallel batteries to mitigate the hazards.
There are better ways, and particularly during recharging, if you have to have a parallel system, in my opinion, you should have ways to get it out of parallel so you can charge in individual string of cells.
Yeah.
And by the way, just one more point, I can find literature that supports these philosophies dated from 1917 all the way to last year. So there's 80 years that have been saying that that's the way to do it.
No disagreement. I have no disagreement.
Oh, you have no disagreement?
I have no disagreement.
Yeah, that's the one other thing I take a little bit of contest here is that I've heard that there's a lot of evolution going on in this, and that indeed that's true. But a lot of the chemistry, particularly that acid, is quite fixed. And the comment earlier about not having smart charge controllers is well taken, and that's where most of them are killed. We, by the way, have a product we've been delivering for 5 years. It's a smart regulator, but I didn't bring it with me.
All right, well, let's move ahead to Stoneman here.
Yeah, what is the physical property that requires the sodium sulfur batteries to be maintained at high temperature? Can't seem to find out in the literature.
Well, yeah, sodium sulfur, you only, let's see, to make a battery work, you've got to get ions to flow inside some sort of electrolyte. And sodium sulfur is only a conductive electrolyte when it's liquid, and it's only liquid when it's over about 400 degrees centigrade. No?
So it's melting point.
There's some controversy as to whether a sodium sulfur battery, if it is let freeze, in other words, go below 400 centigrade, when it's discharged will be damaged. Early versions from ABB and some other companies, I think, did have that problem, which to me sounds like the end of the world. You take your car to the airport, and you're using some of the energy from the battery to keep it hot, even though it's very well insulated. You go away for a couple of weeks, and you run out of energy in the battery, and it gets cold and freezes, and then you have to go buy a new one. So I think sodium sulfur has more chance of being very significant for utility load leveling. I think it's going to come in because it can be used daily.
There's a Mark back there.
I might not get this opportunity to so I have two questions. One is a question of design. Here often you have to design your system properly and things will happen. So here's a question from the PV side of the battery system. One of my two questions. When you size the system, you can look at weather data. You can see that it drops in the winter and rises in the summer. Is it a recommendation from the battery's point of view that a PV system, standalone with no generator that can pop you up in the winter, should a PV system be sized so that the batteries are fully charged in the lowest month? So this absolutely. Okay. That's my first question. I just want to get more depth there. Okay, so there's one question. The other one is related more to safety. It has to do with the idea of the amps of interrupt current rating that should be on your safety disconnect equipment for battery banks, because we've heard that if you have a battery bank, you might have maybe a huge rush of current, and that our downline equipment, like the fuses and circuit breakers and so on, may not have the proper breakage rating. Is it true that we need to consider the sort of terminal short circuit current capability of a battery and size based on that? Or even if we have some good inverter cables, like 2-aught or 4-aught cable for 5 feet, does that cause an effect? In other words, reduction. In other words, how do I need to size my safety equipment based on amps of interrupt current when I'm dealing with battery banks? So those are my two questions.
Okay.
First one was about size.
Yeah. Would somebody like to respond to the sizing the battery for worst case scenario during the winter?
So sizing the array.
Excuse me, the array.
Sizing the array for the winter, well, there's no question about it. It still comes down to money. Can I afford to, how much can I afford in load loss? So if you're going to not keep the battery maintained in the winter time, then you've got to decide that I'm going to suffer load loss. Okay, because you're going to have to disconnect your load from your battery.
What I'm talking about is building a battery bank big enough so that it will discharge during a month or two.
Yeah.
I'll have a partial state of charge battery for a few months and then bring it up. My question is, the sulfation issue that occurs during those months, is that a sure thing and a bad thing, and should I size my array to prevent that?
Sure. Yes. If you want the battery to last. But then you're into an economic trade-off of, gee, it may be better to let the battery die prematurely rather than spend the money on the photovoltaics. This is strictly a sizing.
But it sounds like instead of replacing my battery bank every 3 or 4 years.
That's why hybrids make so much sense. In winter, all you've got to do is get your battery up once a month to really stop the worst stage of sulfation. So if you can run a gas generator, even though it's a fossil fuel and not totally desirable, it's the engineering concept of designed for 100% and it costs you 100 grand, or designed for 98% and it costs you 20 grand.
But there's also the issue of smaller systems that are not home systems, standalone telemetry systems or something.
Then you've got to design for the whole.
Sure.
Okay.
Add lots of modules.
Well, maybe one or two.
Okay, and the second portion of your question again?
Was dealing with the amps and interrupt current problem.
Oh.
How do I size my equipment?
Yeah. That's a pretty basic electrical engineering problem. It's handled by electrical engineers every day, and it's just solved by Ohm's law. The current is equal to the voltage on the resistance, and it comes down to the internal resistance of the battery and the internal of the resistance of the connections and the resistance of the cables. You can look up your cable resistance in a standard handbook like the National Electrical Code. You can get internal resistance of batteries if you're lucky from a battery manufacturer, and you can work out what sort of protection you need. My feeling is that we're probably overreacting a little bit at the moment, from going from some people who have in the past advocated no protection, and I won't mention any names, or going to the place now where people are talking about needing 200,000 amps of protection. If you actually look at real batteries, generally you'll find that a single block can probably do not much more than 5,000 or 10,000 amps. And when you add some lead link on, that's going to go down. Even the biggest of the FNCs can only do about that level. So the answer is just sit down and work it out.
I have one more thing to add to that, though. One of the most important things is look at the time delay for the fuse interrupting capabilities. Okay? And then you also need to look at what is the voltage drop, or what is the resistance of that fuse. You can buy, that's why you see these guys put together these switches with the very small fuses. Okay? Smaller voltage drop over the fuse. You need a fast-acting fuse. These things can pass tens of thousands of joules. That's a watt per second. Okay? When you oversize your cables, you have such great low resistance drops. As soon as you short that out, you can draw a plasma arc with some of these big batteries. Okay? That plasma arc you may not be able to extinguish. And plasma arc, if you look at it, it's going to burn your eyes, etc. So you need to fuse the source. Okay, so that if somebody touches those cables together, it's not live anymore. Okay, and it needs the time delay for the interrupting capability of the fuse, and they have charts. The fuse manufacturers have graphs and stuff. You can look at how long it takes to flow a certain current, size that for the battery.
We typically want to size that fuse so that if we have an inverter that says the size of level X, we want to allow some decent surge going on for a minute or so.
Oh yeah, no, we're talking a 100 amp hour battery can deliver 8,000 joules. Okay, if you've got a 1,000 amp hour battery, think about how many joules you can deliver. That's watts per second with a good cable. Okay.
I think there are two issues there. One is make sure you get the right fuses. They have to be fast. They should be DC rated so that they can clear the fault.
Absolutely DC rated. It extinguishes the plasma when the fuse blows.
Right.
Okay. They've got arc quenching stuff in there.
Yeah. And now another issue that comes up is how is this thing going to fail? I've seen a lot of installations that have a battery bank and they have some gigantic wires coming off from them, and they go about 10 or 15 feet through metal conduit, and then they end up in a fuse disconnect, and they say the battery bank's fused. But I've also seen faults in large industrial systems that I've worked on. Cables this big in a conduit, and when the conduit was installed initially there was a little bit of scrap metal or something that just got in there, and over time it wore through and got through the cable. So a key thing is to try and get your fusing as close as possible to the battery bank. If you have a big bank with multiple strings, fuse every string. And that way you can start getting at the other problem of someone even dropping a wrench on the
So are you talking about physically getting a nice fuse that's got some holes in it there and bolting that to the bolt of the battery?
Sure. Something like a Class T current limiting fuse, something large, 10,000 amps AIC.
We're talking about right at the battery terminal?
Yes, that's the safest place to put it because every piece of wire downstream is a potential problem.
There are some problems with that, I think, that haven't been resolved, and perhaps the industry group here could work on it. And that is, do you put the fuse in a fuse holder? Some things that have been evolved for the telecommunication industry are particularly clean solutions to that. Normally you have the metal links that go between the cells, but you can buy from Buzzman a thing instead of a metal link that's actually a fuse that's rated at 20 amps, 100 amps, 600 amps.
Before we take another question, Bob had a comment.
Thank you. There was a comment made a few minutes ago about voltage regulators and charge controllers and set points. I think there's a misconception that if the battery manufacturer states these are the right set points, they are correct. Or if the charge controller manufacturer says they're correct, they're correct. It turns out that 80% of all the charge controllers out here sold today are the on-off type. And I don't know the single battery manufacturer who has looked at that algorithm, and I have worked with one in particular, a very large battery manufacturer, who specified the set points, same as the charge controller manufacturers. And in 2 years, the batteries were at 30% of rated capacity, with less than 5% daily depth of discharge. And the battery manufacturer then admitted freely that they didn't know what the right set points were. And Sandia, Steve here in particular, is doing extensive testing of charge controller to determine what the set points are. It's critical for sealed or gelled batteries to get those set points correct. And to my knowledge,
We're not saying on-off controllers are bad. I'm just saying we need to understand how to use them better. Okay? They're good. They can be used just fine with the products we got. They just don't know how well the batteries accept the charge now that we have the right set points.
So what about hid logic or fuzzy logic or when's that
Common
coming in?
$50 controllers here for some of these systems.
Yeah, no logic.
Well, but we're trying to protect thousands of dollars of batteries.
Well, okay, but good salesmen sell these people a good controller.
Yeah, why are these all...
Okay?
the point is you cannot assume that those set points are correct. And the other point is, until Steve completes his testing, I don't think anybody knows what those correct set points are to properly charge, particularly sealed batteries.
We will, you keep bugging your manufacturers, battery manufacturers for the application notes. You've heard this now. Keep asking them for these application notes and we'll get them done. As long as you tell them you want the product, we'll work with them to help it get done.
And by the way, the set points don't necessarily control the voltage at the battery.
Right.
So if you're going to tweak it around, tweak it so that you're looking at the battery terminations, make sure the connection, that's a real important thing. If you got voltage losses potentially in there, and if you're looking at the controller and not looking at where the battery's at, you can have some serious differences.
These batteries end up undercharged. And for once, I'd like to see us kill batteries from overcharging them. But a lot of them, seal batteries get overcharged for sure too. But on a small system, even on a small system, a good voltage, a good, well-designed installed system of 150 millivolts drop between the charge controller and the battery if it's not right there at the battery. Okay? Well, that can make or break a system.
And what Steve is saying is true. I've seen it happen in many systems, which is why you should consider charge controllers that have remote sensing.
Absolutely.
Two wires that don't handle any current, they just go to positive and major positive and major negative on the pack. They're just there to sense voltage at the battery so it neglects all the ohmic losses and the heavy cabling moving heat.
That allows you to put all the fuses you want in the world, and that thing is going to still regulate your batteries properly.
Those low current cables should also be fused, even with a small fuse is strong.
Quarter amp fuse or something.
Because they'll smoke.
Yeah, instantly. Okay, another question. Joe.
I have two things. So one is to stop this issue of cable loss. I've read charts that say 2% or 5%. And what's appropriate?
Cable loss is like having too much money or being too good looking. Efficiency is just like that. You can't have a system that's too efficient, all right? The bottom line of my thinking is you spend a lot of money on modules, charge controllers, and batteries. In comparison with that, decent wire and decent connections is extremely cheap. I size all my systems for 2%.
There are times when you can sit down and figure out the cost effectiveness, whether I need to add another module, and whether I need to go up in wire size.
Yeah, it's a standard, for larger systems, it's a standard calculation that we do to work out what the wire size is and how many more PV modules we could add to replace that. And the utility does it too. They work out how much energy they lose going along the street from having a certain wire size, and they put that against the copper.
What costs more, the copper or the module?
Yeah, and so that's
General, a module.
right. It's a standard economic procedure that's done in electrical engineering. You equate the economic cost of a smaller wire size to the cost of the copper and optimize it.
And there's also, we have options now. The only place this is normally really a problem is in the array to the battery. Most everything else is compact. Now you can have a 12-volt battery and run your array at 48 volts by using electronic power processing, something like Rob's maximum power point tracker or a linear current booster. You can defeat the ohmic losses in these cables by running the array at a higher voltage using an electronic circuit to convert that extra power that is manifest as voltage into current for the battery. I'm doing this with a wind machine. It allows me to use relatively small gauge wire and run the wind machine at about 36 volts while I'm charging a 12-volt battery. So there are technological fixes that are going to help us get these arrays further away and still defeat the ohmic losses in the cable.
How much are they?
Which? The linear current boosters? They're anywhere from about $200 to $600, depending on how big you want it. The one I've got's 100 amperes. It'll take 200 volts on the input, 100 amperes out the door into the battery. It's about $600. Bouvier Sun Selector makes it.
You can use thin wires on that?
You can use thinner wires because we are running the array at, say, 60 volts rather than at, say, 16 volts.
You need someone to design it for you still.
Yes.
Maybe in all this technical stuff, this question's been answered, but I'd like to make sure that it's clear to me. The battery manufacturer specifies a certain depth of discharge as I presume, the maximum depth of discharge before charging. Is that correct? Okay, then is it better for that battery to discharge that battery to that point before recharging it, at least on an occasional basis?
No.
I see guys with machine drills sitting there running until they stop.
Whoa. Different situation. There is one type of cell that has a memory. In other words, if you don't use it, you lose it. And that is the small sintered plate nickel cadmium flashlight batteries. Don't confuse that memory effect with lead acid batteries, pocket plates, fiber nickel cadmiums, nickel irons, or nickel metal hydrides. The only battery that has it are those small NiCad sintered plate flashlight batteries. Those are the only ones that benefit from routine deep cycling. Otherwise, the shallower the cycle, the longer it's going to last, regardless of technology.
I do have one other thing to add here. This is something that has evolved from trying to develop these application nodes. When we talk about the low voltage disconnect, we have also, people have discussed, well, we need to compensate it for our rate of discharge, okay? We also need to think about how long that battery spends down at that rate of discharge, okay? When someone says, okay, set the low voltage disconnect at 10.5 volts for an 8-hour rate, 10.8 volts for a 20-hour rate, 11.8 volts for 250 to 500-hour rate, okay? If this gentleman in the back here is going to run this system for 3 months, okay, at a low state of discharge, that's greater than a 1,500-hour rate. That means you need to compensate that low voltage disconnect, or you need to oversize that battery bank big enough so that your voltage on your system voltage doesn't go lower than the recommended decrease. Otherwise, you're severely discharging those batteries. Did I get across that point about the extended time of that low discharge rate? And needing to raise that set point? So a lot of these batteries end up greatly deep discharge, much farther than we even understand right now.
Okay.
Simple question. What's the best way to clean batteries? Water, no soda, no...
No. If you have the acid on top, then neutralize it with soda and water.
But don't get it in the battery.
Right. Yeah. 1 pound of baking soda, 1 gallon of water will give you plenty of neutralizing agent.
But be very careful when you use it on the top of the battery.
But any in that battery...
No battery is fully sealed on the top. There are holes where the posts come up. There's a filler hole. If you slop baking soda down in there, you're neutralizing the electrolyte. And that's not what you want to do.
But if it's just to wipe the dust off, a damn rag.
Can I go one step further than that? I was running 70 batteries. I built my last battery box to hold 24 L16 to go to the point. I have 90 pound pressure. I clean my top of my batteries off real good about once a month. Once every 2 or 3 months, I very carefully go over just the battery terminal with with baking soda. And I leave it on. So the next time I get ready to run the hydrometer test, I wash my batteries before I run a hydrometer test, so the battery top is absolutely clean of all dirt. Don't get dirt into the battery acid. How are we going on that?
Yeah. Does it work for you?
Anything wrong? Can you improve on that system?
Well, yeah, you can have a battery that doesn't need a hydrometer.
Huh?
You can use a battery that doesn't need a hydrometer.
Well, we're talking about a lead acid battery.
He's already got the batteries.
I know.
We remember, we're talking about 2 banks of batteries, nickel cations and lead acid. Should be 2 different groups for one group and one for the other. We are confusing the thing back and forth on this.
Okay, to answer your question, if this works for you, to me, it sounds extremely labor intensive. But if it works for you, that's fine.